Hello, I'm Kfir Dolev. I'm a student of Patrick's. And recently, I'm going to tell you about a work that I put out on Archive recently. It's basically like a step in the direction of, let's say, inspired by the following observation. Which is that the motion of stuff, the motion of matter, is very different from the motion of information. And hints of this pop up everywhere. Like, for example, you have these evanescent waves that leave the light gun. The information never leaves the light gun. Or recently, in a result by my former advisor, Eduardo Martin Martinez, he showed that you can send a signal without actually sending energy. So without actually having a particle carrier. And so this might lead you to ask, how does information move around as opposed to stuff? So the main objective is to characterize how information can move around and be processed. In space-time.
What does stuff mean? Does it mean conserved quantities?
In all of these degrees of freedom.
Yeah, but
fields.
technically what it is energy, momentum, charge. Oh, I didn't want to stop you, just.
Yeah, I'm not. When I'm saying this, I'm saying that usually we have like this classical picture of stuff, like waves or particles or blocks or whatnot. And then we try to think about the quantum version in terms of that. And I think that often can lead us astray. Anyway, that's not the point. Okay, so we want to see how information can move around and be processed in space-time. So to answer this question, well, first we need to ask a specific question. So for that, I want to introduce, I want to define a few things which will provide a useful language in which we can ask questions. And that's the language of relativistic quantum tasks. So, and space-time, relativistic task, and four things. It's a set of n input nodes. Instead of n input systems. Instead of n output points. Okay, this is very pedantic. These are input systems, these are input points, you have a set of output points. Then finally you have a set of output systems. OI. the picture that you should have in mind is something like this. So I have, so let's say that this is space-time. I can do this. Very tall. Let's see. So I denote the input points as points with inward arrows. And then the output points is points with output arrows. A lot of space here. Okay. And so the last thing that the task consists of is a channel. And I1. And all this is very pedantic, but I just wanted to be extremely clear. So the way that you should view this as a game between two players, Alice and Bob. And Alice and Bob are not individual people, they're agencies. So Alice has many agents that she can send and move around, but they can only communicate under the constraints of causality in space-time. And so this is a game between Alice and Bob, and the game is that Bob feeds in quantum systems, I, at point Ci, and he requests that Alice, or he hands over to Alice's agent this quantum system, and he requests that Alice hand back at these output points quantum system, J. And furthermore, he challenges Alice to implement the channel N on the system. Okay, so that's a relativistic quantum test. It's there.
M is any Lorentz space-time?
In this definition, yes, but for these theorems, it only requires that it has no close timeline groups.
I have a quick question. Is the channel restricted in any way to be somehow relativistic with respect to the separation of points, or is it allowed to be
So,
anything?
okay, so yes, the paper is called Constraining the Doability of the Task. So a task can be anything. Sometimes it's not doable. Right. So in particular, it could be not doable because it violates relativistic stuff or quantum stuff.
Right. I understand that. I guess my question is just: Are you allowing these? So you're certainly allowing communication between, say, I perform a projective measurement of input qubits or something, or I prepare one of the input qubits in a state and I send that information along, a photon from Alice to Bob.
Sure.
That's all allowed and it has to follow the rules of causality and all those things. I'm just wondering if similar rules apply to the actual channel end, or whether that thing I just described is to be considered as part of the channel. I guess I'm confused about what the channel is allowed to do and what it's not allowed to do. Maybe.
It's any CPTP method.
It's okay.
Any
Anything.
CPTP method.
Okay. All right. That's my question.
So this is the challenge from Bob to Alice. And so now it's Alice's turn to try and complete the task. And so to do this, we make rigorous the notion of a plan. And a plan is just going to be, where in space-time is Alice's agents going to meet, and what are they going to do? And then we're going to say that a task is doable if there exists a plan, which if you execute it, gives you the right channel. Has the same things as the IO input, IO systems and points, and it has these new things, which I call gate points. So whereas before we just had input points and output points, now we're going to have points in space where calculations are actually being done.
So you basically you're embedding what we usually think as a circuit in space-time in a way that's consistent with modality.
Exactly.
Okay.
Just think of it as a normal quantum circuit, but just take the wires literally as curves in space-time.
I thought you were having to do, I thought you could do that, and in addition, you had an additional channel that you could also use.
Oh, no.
Yeah.
Okay, yeah. So you specify the gate points, and then you specify a channel at each gate point. So for example, if I have some gate point that takes in 3 systems and outputs 2 systems, this would be the channel. It would have some channel describing exactly what happens there. Okay, so, and then you need to specify trajectories. So in this case, maybe something like this. Of course, they have to follow. They have to obey causality. And then the last thing is you specify. The last thing you specify is auxiliary resources. So Alice could have arranged that some entanglement gets shared between several of the gate points. This is allowed.
So you can have as many of these EPR pairs as you like, if you have to have time to prepare them. Is that a bit strange? Or are they just lying around in the space time for you to use it?
Sorry, where are the pairs here?
So Alice has some agents down here at minus infinity, and she's making her plan. And she's saying, okay, in order to execute this plan, we're going to need to share this many.
You get to start at minus infinity.
Yeah, that's right.
Okay, so you can really have them everywhere, as much as you want.
Yeah.
Oh. Okay. But if you, so in particular, you can teleport anything. I mean, you can use teleportation with
That's right.
arbitrary amounts.
That's right. Yeah. And in particular, here we're not.
No, of course.
Yeah. In particular, we're not going to make
you we only get to start at some finite time.
Oh, I see.
I'm not going to be worried if I'm going to allow infinite amounts of entanglement. So you might say, okay, this is going to cause black holes, but I'm going to say I didn't think about that yet.
I can use entanglement. Can you use entanglement? Sure.
That's just a practical. Maybe I should say that once you come up with this plan, this induces a channel, right? Like Bob feeds it in stuff, Alice does a predefined thing, so the output systems will have some state, so this specifies a channel. So relativistic quantum task is doable if there exists a space-time circuit whose induced channel is that of the task. Okay. So that's all the definitions. Are there any questions so far?
You don't have any restriction on how much energy you have, or not? What's this highest energy density?
Nope. Yeah.
There's no gravity.
There's no gravity, it's a static space. Yeah.
Oh, static? There's no battery.
Non-dynamic.
No, sorry. I'm not. Okay.
Do you restrict the dimension of the space-time?
I don't think so. Yeah, any space-time will do. So,
I mean, with me, like, I'm surprised if you can have arbitrary high spatial dimension. I thought, like any circuit, you would embed some.
Fix it. Fix the dimension.
So for
I don't think you get to take, you get to change the dimension of the space time after you specify it.
Okay.
the task is on the space-time. here's some examples that are familiar, almost insulting. Okay, so suppose I gave you 2 tasks. One is I feed in a state here. The other is I ask you to return the state here. The other task is I feed in a state here. I ask you to return it here. Okay. This task is doable. This task is not doable. The space-time circuit that implements it is trivial. Do this. Here, there's nothing you can do. Okay. So that's no signaling. Oh, God. This is going to okay. The next thing we can talk about is no cloning. So if I feed you a state, so here's a task. I have 1 input points, 2 output points that are also fed in some data. So you can think of them as 2. Yeah, the input point and the output point are at the same point. And each of these output points are going to get fed a bit, which is the opposite at the 2 output points. And basically, the task is to return the state at this point if the bit's 1. At this point, if the bit is 0, can this be done?
Yes.
Yes, very easily. This, great. That's enough. Okay. And what about something like this? So it's the same stuff. In this case, the answer is no, because it would violate no cloning. And the reason is just that it's a little subtle, but if the input bits here somehow got messed up and both of them were a 1, then there's no way for these 2 agents to signal to each other that they got the wrong bit. And so they'll both return psi. But then you clone, so that's a contradiction. So
it's not a contradiction if you throw that coin earlier and send that message. Okay. You say it's a contradiction if the random B was decided locally.
if I decided B locally here,
Okay.
yeah, I mean, it would still not work. That this is doable or not has nothing actually to do with B. It's just.
I just mean I don't know how you formulate this, but like I could decide B as the input point.
Yeah.
And then I decided where I send this thing. That's totally okay.
Yeah.
I think
that's
about the notation.
Yeah.
But that
When
is
you're
not
asking us whether you should swap the state of psi onto some auxiliary bit that you put in at these output points, and you decide whether or not to do it depending on some coin little b.
Yeah, that's right.
So you just have the world line of the state psi, and then you decide to solve it into this other thing depending on the coin.
Nothing here is interesting.
Well, I guess so.
So right, it's just so you're used to this notation.
It's interesting.
Oh, no, okay. Okay, so now for the last mundane task. This is called the routing task. And it's basically one input point is given the state, one is given a bit.
So when you say bit, you always mean classical.
I always mean a classical bit, that's right. graph. These applied codes. Okay, the task is just if b is 0, return side here. If b is 1, return side here. It's a very easy task. You bring these things together here, perform an operation, swap it depending on which direction it needs to go. But notice that in order to do this, you had to use the existence of this space-time region here. Use the fact that this was not zero.
Sorry. Here, Alice decides what B, right? But on the middle, on the no cloning test, that was Bob who was deciding what B, right?
Bob's always deciding what B is.
Even here?
Yeah, even here. Bob feeds in.
Oh, I see. Bob is not necessarily at later times. Bob is not necessarily at later times.
Oh, he picks up the systems from Alex at later times to check if she did the job right. Okay. Now we get on to something interesting. So all this has been describing the motion of information. Now we can talk about the processing of information. And so there was this result that was debated for, there was this issue that was debated for a few years about whether or not it's possible to do position-based quantum cryptography. And it basically culminated in the following result. It's a very pessimistic field.
I don't know why you didn't like no routing and just the other example where it doesn't work. This is really cool with the general.
That's true with the theme of
You know,
pessimism.
yeah.
So the boils down to the following question. Are there channels that can be implemented in circuits that look like this? One, two. So, are there channels that can be implemented in this circuit here, but not here? So here the particles, or here the information had a chance to meet. Here it doesn't. And so the question is, maybe, some additional channels can be implemented here that can't be implemented over there.
The point is that the right side is supposed to be just squatting.
I think you can actually implement this in a flat space-time, but you can implement this on the ADS cylinder, for example.
Oh, I see.
Yeah, the ADS cylinder you can construct input and output points that don't have this region.
So you want a situation where it's possible to send a signal from any of the input points to either of the output points, but nevertheless there's no chance for those signals to meet.
Right.
I see. So you need something topologically non-trivial.
Yes.
So the answer to this was no. Anything you can implement here, you can also implement over there. But there's a catch, and the catch is that you need to share entanglement between these two for certain channels. Okay.
What did BPQC mean?
Position-based quantum cryptography.
Position.
So if we're back to, if we stipulate that I'm not allowed to have any entanglement beforehand,
Yeah.
then you do need to be able to meet beforehand.
Right. In order to do any channel. Okay. So, I'll prove this in a moment, but first I want to state what the result of my paper was, which is just a generalization of this thing.
Could you explain for the people who don't think that way, why is this called no
Position-based conflict.
conflict? Yeah.
Let me explain it here. This is one of the applications, and it's not too difficult. You can ask me after also. It's like a two-line explanation. Removal theorem. So basically, this theorem just states that whatever circuit you draw, if you used gates, you didn't need them. They were completely superfluous. All of the work can be pushed to the inputs and the output points, but this is going to cost you in entanglement. How much entanglement is left to future research? But the fact that this is true is actually kind of interesting. It actually ends up being a sanity check, or ABS, where you can have the bulk and the boundary having causal structure that doesn't match. I mean, like yeah, you can always signal. The signalability between 2 points on the boundary is always the same, whether or not you're allowed to go through the bulk, but whether or not you have these like fine regions where that can be signaled by multiple points and can signal multiple points, that's different between boundary. Okay, so the theorem is consider T with points define again, it's very pedantic, but I have a short attention span, so this is necessary. Okay. Feature is one. So it's just this, I'm defining a function which takes in pairs of inputs and output points and just tells you about the causal relationships between those two. I mean, it doesn't even tell you all of that. It just specifically asks. Actually, it does tell you all of that. So the theorem is then the doability of the task depends on Ci on I only through F. Okay. So this highly constrains whether or not a task is doable. And we can check in this case that this makes sense. First of all, let me ask, are there any questions?
Yeah, what does this thing say?
Sorry, yeah. You have a task, and the task involves inputs and outputs, and depending on where they are, they'll have different causal relationships.
Yep.
And what this says is that only a very small fraction of the data about the causal relationships between the points actually matters as far as whether or not this task can be accomplished. And specifically, that data is
Is what?
is pick an input point, pick an output point,
Yeah.
and ask, are those two, can the input point signal the output?
Isn't this all the data?
Hmm?
What data is not included in this?
Whether or not regions like this exist.
I see.
Input relation
Yeah.
to the output.
Sorry, so the, you mean you need to know that for every pair?
Yeah, that's right.
That's what.
Yeah.
That's what.
And it has to depend on this minimally. Just apply the no signal task to a pair. You can always change the doability based on that.
So the example there is if I move this, so I could have this pairwise relations all the same, but I could have a case where that intersection
That's right, yeah.
is no intersection.
Yeah. Basically, the proof shows that if you give me a protocol, I can construct another protocol that gets rid of all of the gates. And if it gets rid of all of the gates, then it always works when you have those causal relations. Okay. So now for the proof.
So if you give me a quantum circuit embedded in the space-time,
Yes.
is it clear there's a way to move the inputs and outputs around without changing F so that all the gates become disallowed?
All of the gates become what?
Disallowed.
Disallowed. It's not clear, no. In fact,
Like, I'm having a trouble. Is this exactly equivalent to removability of gates?
I think the answer, I mean, in a particular space-time, you won't be able to move the points around to get rid of this stuff. You might have to take the task and put it on a different space-time.
Space-time is not fixed?
Well, I mean, you can have the task be exactly the same except for, so there's the same number of input points, the same number of output points. They're fed the same thing, they're required to return the same thing, but it's just that you place them on it.
I see. So if what you have to do is there exists a space-time such that without changing F you can remove all these intersections, and therefore the task can be implemented without any gates. And
He just directly proved gate removal. It's not that he proved this.
So my assumption is
yeah, but is it the same as gate removal? Is the question.
I don't think so. I'm not saying anything about what kind of space-time.
it's not about geometrically whether you could remove the probability of having gates. It's to show that you don't need the gates.
Right.
But yeah, but the point is that the
It means you can do it by free photons.
sure.
Yeah.
Never interacting.
There is a lot of causal structure here, and he's saying that just like a little bit of that matter.
That's fair, and I'm asking. I guess I'm asking why he's calling it gate removal theorem and phrasing it like this. Is it the case that gate removal and this statement are exactly equivalent? But like this seems like a very different statement from gate removal. Right?
What statement
No?
seems different?
The statement of the theorem.
So you do gate removal one by one.
I think this is a consequence
It's a
of
concept.
gate removal,
Yeah,
but it doesn't necessarily imply gate removal.
exactly.
Is that your point?
No, possibly.
I think
So it does imply
I
in
think
that.
this doesn't plug
It does imply
It's
there.
based on where the gates are gone, right? By just, since you're not constrained
yeah,
by
that's-
identity equations or
yeah,
anything, you
yeah,
can just
yeah,
make two that miss each other
Yeah,
and
okay, so
force
yeah,
things
yeah.
to.
Very cool. Okay, good.
So is this like a Merriman-based quantum computation? Because like you're removing the gates and instead using entanglement.
I'm actually not really sure what measurement-based quantum computation is. So I'm not
Maybe
qualified to answer that
a
question.
simpler form of that question is if I have access to whatever semi-classical space-time I want, and I'm allowed to perform these sorts of move photons around, do I automatically have a universal quantum computer?
Sorry, can you say that?
I
I think that
If all I have is a space-time and I have input and output qubits, and maybe I also have entanglement, do I automatically already have a universal quantum computer?
I mean, I'm kind of assuming that you have the ability to do whatever computation you want already, right? It's not that.
Okay, then I'm.
I think what we were wondering about, I mean, I think that the way that you utilize the entanglement resource
Yeah.
must involve increasingly complicated measurements or operations that.
Yeah, a lot of teleportation. I can actually
Yeah,
show you
but the
precisely.
teleportation isn't going to be the dumb one where you just project, you just measure at the Bell state basis. It's going to become a really difficult one for which you actually need a quantum computer to just do that.
Oh, sure. Yeah.
Oh, okay,
Yeah. That's right.
okay.
So I see. Okay. Yeah. If you have entanglements, you don't need parts of the geometry. So now we do the proof for this thing. Oh, sorry. So okay, I want to prove this, but this is a complicated proof. So instead, I'm just going to prove the already known result that any gate can be applied. Any channel can be implemented here. And my proof is basically just inordinate recursion of this thing. So this, if you like details, then you can read my paper afterwards. Or conceptual, you know, interesting stuff. It's got.
You're trading geometry for entanglement. What if they're the same?
I think there's actually something deep here, but for reasons that. Oh, I mean, okay, we all think there's some. Let me just say the proof. Okay. Putting this up in the that's not the proof. That's other stuff. This is the proof. Okay, so in order to do this, you need a different kind of teleportation that's called port-based teleportation. Sorry, let me do that over here so that we can take in one blackboard. So, port. Yes. Thank you. Okay, so in port-based teleportation, you have two people, Alice, Bob. Alice has some system, Bob has some system. There's some state that's collectively on these systems. And then there's some resource which lives on a these many other auxiliary systems. And what state are these in? Well, that's a detail. They're in some complicated state, I think. These things are called ports. So port-based teleportation means that if Alice and Bob are space-like separated and they have this set up already, that means that just by local operations and no communication, they could end up in the following scenario, where Alice still has her system. She has all of the ports, Rn. Bob has nothing except for an integer I. And then the state psi AB is actually now all held by Alice, with the part that was in B being randomly chosen to be in port I.
Randomly chosen, say again? Oh, say it again.
Right. So they do some stuff.
Yeah.
I is randomly selected from 1 to n.
Why is that? Okay.
The state on B appears in port I on Alice's side. Yeah. And this works to within an error of 1 over root n. So now,
The overall state's like a sum of psi tensor I or over I.
okay, overall state.
Is the overall state on the bottom the sum over I of psi tensor
Always with more.
the state I?
Uh,
I'll let you.
I think, I don't know if it matters.
I was just, yeah, I'll let you.
I think so, but I think like you could also say like in the measurement happened. Yeah. Okay, so now we want to show that anything can be done on this circuit. Okay. So Alice and Bob do the following things. They start with the systems A and B. They're fed in here. I'm changing a little bit the notation. Like here the game is between Alice and Bob, but for simplicity I'm going to say that the two different inputs are now Alice is at this input and Bob is at this input. All right, so Bob stands here. Should have some shared resource.
This Alice and Bob have nothing to do with your previous Alice and Bob, right? In the sense that Bob
yeah,
is
that's right.
formulating a challenge for Alice.
Yeah.
So, but
Yeah, they're on the same team.
now
Yeah,
they're on the same
now they're on
team.
the same team, that's right.
Very touching.
The relationship is very volatile.
And it's true, Alice just stole everything from Bob.
All these guys.
Oh my God.
You will get a t-shirt.
So, the first thing that Alice does, they're all, okay. This all happens at this time, First thing that Alice does is normal teleports A over to Bob. So, side A, B. Okay, so the effect of this is for Bob to have both A and B, but the A system is going to be encrypted because some random pally happened to it in a teleportation. And Alice has these bits A and B. And there's some other resources that I'm suppressing. So the third thing is Bob ports teleports. AB to Alice. So the result of this is Alice has the bits AB, and then she has A prime. I and Bob has the integer I. This contains the state XA, ZA, psi. Okay. But Alice has the bits A and B, so she can remove this encryption by applying it to all of the registers. So all of the other ones except for the ith one will contain junk, but the ith one will then contain the original state. So this is pretty miraculous, that the original state has been moved to Alice, but why is no signaling not violated? Well, because Alice doesn't know which one of these ports actually contains her state. So, well, what they were trying to do is apply the channel N to this state. So what Alice does is she just applies the channel N to all of the ports. So this goes to...
Sorry, I missed something completely.
Yeah.
Why can't we just set into one here so that she has only one port and does know where?
The fidelity. Yeah. You could. You just get garbage. Okay, so Alice applies the channel N to everything, so that means this will end up with the channel applied to the state. And the last thing that happens is, okay, so all of this happened at this time. No time elapsed for these three steps. And so they're still left with this communication. They're still allowed this communication. So what do? Bob sends I to, let's give these C1, R1, R2. Bob sends I to R1 and R2. And then for all J necessary. Alice sends A prime J to R1, B prime J to R2. But that means at R1, Alice's agent has all of the A's and I. So they're able to figure out which is the correct system. And similarly at R2, they have all of the B's and I. So they can figure out what the right system is, and then they can just turn it into a system.
Here, can I ask a basic question?
Yeah.
So is the point here that Alice can receive the state, but just doesn't know what it is, and so can apply operations to all of the qubits while she's waiting to figure out which state it is? So for instance, Alice has some computation to do on the state that Bob has, and doesn't want to wait very long to do it, or she just gets all of it?
Yeah, she doesn't have time to do it. Like this needs to happen like immediately because they don't have time to bring the two pieces of information together. So the point is that they've managed to arrange things in such a way that Alice holds all of the state, but she doesn't know which one of the registers contain that state.
But the idea here is that she can still do like computations with whatever state she receives. She just doesn't know which it is until Bob can communicate it to her.
Yeah, she doesn't know which it is until.
Okay, cool, thank you.
I'm sorry, I missed what the task was that has now been accomplished.
Okay, right. So the question is, can every single channel be applied in this kind of circuit? That's the question. So that's the same thing as saying that everything here can also be accomplished over here. Here you know every channel can be accomplished because you can bring the two pieces of information together and you can apply any channel.
Oh, I see. And here Alice does it before she sends the stuff.
Right. Yeah. So that's the no position based on cryptography result.
And back to the earlier question about needing a quantum computer, at the end of all this, you do need one, because you need to be able to apply to undo these gates.
Yeah, I mean,
locally.
yeah. Although in order to apply this channel in the first place, you probably need it.
Yeah.
Can you comment on the necessary resources for and what's true, what's not true?
Oh, the resource cost of this thing?
Yeah.
Yeah. So that's a good question. It's very important. So in order to do this required entanglement. I've actually, it turns out that the amount of entanglement that it requires an exponential number of qubits in the total size of Alice and Bob's system. But it's an open question as to whether or not that's actually
Is that
necessary.
really true for this example? Like, don't you just need, if you started off with A and B being qubits, you just need this fidelity to be high, right?
Yeah.
And so if you want to recurse, it will grow exponentially.
No. It's exponential at this point. Yeah, the precise proof I don't actually recall at the moment, but yeah, when you have many gates, it's just much worse.
Sorry, is it exponentially in what?
So the total number, it's exponential in the total number of qubits of Alice and Bob's system.
So you're saying that each gate Ri, sorry.
Oh, this is a D over dimension, I think.
This is a deal. Okay. That would do.
That helps.
So it actually needs to be d squared, d is the Kfir Dolev.
But I think what I said earlier was not the right case, right? In the sense that the quantum computation is actually it's just done locally at Alice's site.
Yeah.
You still need a quantum computer. It has nothing to do with like the fancy measurements of the. It doesn't really have to do with the teleportation. The quantum computer computation is done after the teleportation has already been performed, and it's then done locally at Alice's registers. It's just doing the same old algorithm computation.
Okay. So here's some interesting. Okay, I guess now I can explain this position-based quantum cryptography business. Why is it called that?
Oh, I'm sorry, but I guess you could be front-loaded into the teleportation protocol. Like you could just make, you could just perform the teleportation in such a way that it already includes the appropriate unitary on A. Is that right?
Bob?
Or whoever is performing the teleportation. I mean, yeah, I
Not
think
sure.
it's step 3.
Sorry. I think Alice needs to do it.
Because she has that encrypted first.
For restricted set, if it's like a Clifford or something, you don't need to. Okay. Actually, yeah, maybe I'll stop here and then I can explain the position-based cryptography to anyone who's interested. Okay, thank you.